Hey everyone, we're going to look at common and natural logs. We're going to be looking at graphing them as well. So we're going to be looking at base E and base 10 logarithms. Thanks for watching. Don't forget to like, comment, and subscribe. E is a number kind of like pi. It's just represented with the letter. I guess this time it's English letter. But E is, well, it stands for E's Euler's constant, not Bueller, by the way. Am I dating myself with that right there? That's good. I liked it. It was good. Some good times. Euler was a math guy, and because of him, now we have the constant E, which is used a lot in physics and engineering and these kinds of things. Maybe you care about that, maybe you don't. But there it is. There's a few of the numbers. It's irrational, so it does go on forever and ever and ever. And it never repeats or terminates. So, whatever. There it is. And that brings us to common and natural logs, which, again, we should have seen in 980. So, again, these go both ways. Right, so you can start with log base 10 and go to just a common log of x, or you can start with common log of x and make it log base 10 of x, right? And if we took this even one step further, and it goes for both ways, is in exponential form, this would be 10 to the power of y equals x. Oh, uh-oh. All right, in natural logs, it's the same idea, right? It goes both ways, but again, we can change this even further into exponential form, e to the power of y equals x. Now again, that's the natural log. So when we see a base of e, we usually try to think of a natural log. And when we see a base of 10, even with the exponents, we can go straight into common logs. Sometimes we show that two steps. Sometimes we just go straight from one to the other. So I apologize. That means that we could have another arrow out here like this, and one out here like this. Okay, and again, it goes both ways. All right, evaluate this. Give your answer to 4 decimal places. Okay, you got it. Natural log. All I'm going to do in my calculator is find the ln button. Sorry. May look like that. Every once in a while I'll see one that's capital L, maybe. Right? Then you can put 0, decimal, 0, 1. Then you got an equals or an enter button. Alright, in my calculator, it gave me negative 4.60, 4 decimal places, 6052. Sorry, that's an answer, not a button. All right, the last one was a natural log. This one is a common log, so you're going to look for the log button. Now again, sometimes you have to push second ln. For some of you, the natural log button is the log button, so you just push it twice, maybe. I forget which one it is for log or natural log. And then it's the log of 460, so you push 4, 6, then 0. Whoops. 0. Then push your enter button. Alright, then I got 2.3 decimal places, 6. I had 27, so I'll round it up to 3. There we go. Alright, log base 20 of 0.69. We want to evaluate this, and we'll give the answer exactly. Now there's a problem because some of us get used to writing this in exponential form. So that'd be 20 to the power of y equals 0.69. I can't do base 20 that well in my head, so I'm going to need a calculator for this. If you can do it, though, that's fine. I mean, 4 decimal places. Some of you guys may be thinking, oh, that's not too bad. But for me, it's really bad. So here we go. What that means is I'm going to use the change of base stuff because my calculator doesn't have actual logarithms. So, do you guys want natural logs or common logs? Alright, so base 10 gives us the common log, and it's going to be of that 0.69, and we're going to divide that by the log of the base, which was 20. And whatever that comes out, again, we're going to round that to 4 decimal places. And I got that's a 0, sorry, 0, negative 0.123, and I got 86. So I'm going to round that up to 9. 4 decimal places. There we go. Express this equation as a natural or common log. So the base is e on this. So I know that I'm going to be using a natural log. Now if we were to shift through this both times, so that means we'd have to change this into a straight log. Then it'd be log base e of 3. I'll use a different color there. Equals the x. But log base e is the natural log, which is what it wanted. We want the natural log right there. So we're going to change this to the natural log of 3. And that equals x now. So that's it. Express the equation as a natural or common log. Once again, that's a base 10. So you could take it straight to a log, right? But I don't know. For some of us, it's helpful to see this as a log first. So it's log base 10 of that 13 equals x, because that's the exponent right there. But log base 10, once again, is the common log. So we don't need to write that base 10 in there. Common log of 13 equals x, and we're done. All right, evaluate this. I'm going to do it the long way first. All right, just because we have so much stinking time. I know you guys don't want me to either, right? I'm going to change this into an actual log base 10, because it is the common log. 1 over 100 will make it equal y, so we can change it to something. That's 10 to the power of y equals 1 over 100. And 100 is 10 to the power of 2. So it's 1 over 10 to the power of 2 equals 10 to the power of y, which really is 10 to the power of negative 2 equals 10 to the power of y. So finally, negative 2 equals y, which if you plug that directly into the calculator, it should have given you negative 2 as well. All right, again, we got a common log on this one. We'll skip the long stuff on this, right? So we'll just plug this into the calculator. That would be in the parentheses. For those of you that may need it, that's really 10 to the power of 1/3. When you plug this into the calculator, you get 1/3. This brings up a new rule for us. Not that it matters for us yet, or as far as I remember ever. But as a log, this would be log base 10 of 10 to the power of 1/3. If this ever happens where the base is the same as what it's of, you just kind of cancel those out. So, whatever. Calculate f of negative 1. Okay. Well, the function here, we're just going to go in and replace the x's with negative 1 there. So, it's 2 times e to the power of negative 1. So, f of negative 1. Again, I'm just going to plug that directly into my calculator. I guess 4 decimal places. Not that it's said to, but whatever. 0.7358. That is the answer. All right, graph. We'll do f of x equals negative e to the power of x. I'm going to do that in red, but we're actually more familiar with g of x. Just e to the power of x, right? So, I'm going to do the purple one first because it's positive, not the opposite stuff. But it's going to make the opposite stuff pretty easy for us once we have that down. So I'm looking at x and then g of x for this. All right, and we should be able to see a pattern pretty quick. I'm going to use negative 1, 0, and 1 again. I mean, that's what we would usually do for linear functions, but here we go. So e to the power of negative 1. Actually got 0.36 and some garbage, but graphing the hundredths on a graph this size is going to be extremely difficult. So let's just say 0.4, negative, and 0.4. We'll put it right there. E to the power of 0, just like everything else to the power of 0, is 1. So 0, 1. And then e to the power of 1 is actually just the base value, e, which we'll say is 2.7. So 1 and 2.7 up here. And at this point, it should just ratchet up like that. And this one is going to get extremely close to 0, but never actually touch it, which creates an asymptote at y equals 0. So there's our graph for g of x. We'll label that g of x, but we still need our f of x stuff, right? Well, f of x, I can use the same table on this, by the way, just for convenience purposes. I'm going to take g of x and make it the opposite. Negative 0.4. Oh, I didn't fit that in very well. Negative 1 and then negative 2.7. So let's go and graph those in there. We're squeezing the x-axis on that. One of the other questions I remember seeing on the homework is something to the effect of what transformation is taking place. We can kind of see that that purple line, which is kind of the original e to the power of x, even if you start with the red one, it doesn't matter. Right? If we had shown the x-axis here in green, it's just a reflection. Okay? It's a reflection across the x-axis. So when you see that on the homework, that's what it would be for this particular case. I like to think of Bob Ross, not just because his hairdo is awesome, but it's a reflection thing. I remember seeing him do this, and yes, I am a nerd, so I watched Bob Ross. Sorry. So he did a painting where he did a bunch of trees like this. And then what did he do? This was over water, so then he just put the line for the water right there. I mean, he did a bunch of other stuff and made some happy trees and stuff, but you understand that that's a reflection over that up and down. If it were side to side, then it would be more like a mirror reflection. And I don't remember Bob Ross ever doing that, so sorry, I don't have any good examples for that. All right, I'm going to move on now. Graph and find the domain and range. Again, I don't like graphing with logs straight across, all right, even though you could with a calculator. I prefer to show this as a exponential. So 3 to the power of y equals x minus 3. Again, I don't like that x minus 3 stuff. So what do? Happy trees, right? There we go. Just make that plus 3 on both sides. Now I got the x all by itself. Bob wouldn't like that. He didn't like his trees being alone. But in any case, this allows us now to make our table. So we got x's and y's. We're solving for y, so we'll choose values of, we're solving for x, so we're choosing values of y. I'm going to start with y is 0, because that's a pretty easy one. 1 plus 3 is 4. When y is 1, then it's 3 to the power of 1, which is 3, plus 3 is 6. That gives us a couple values to start with. Let's try another one. Let's see. Nope. If I chose 2, that wouldn't work. 9 plus 3 is 12. But it does give us a good idea of where it's going. So I do need to get more space first. I'm going to have to go in the negatives. So negative 1. That gives us 1/3 plus 3. So as a decimal, it would be 3.3 or 3 1/3. So let's graph these points then. 4, 0, 4, 0, 6, 1, 12, 2. You know, you could kind of visualize where that's going to be. And then 3.3 and negative 1. About right there. And that should be enough, hopefully by this time, to show the pattern where it's going. Even without finishing the line, where is the asymptote on this? 3. Positive, yeah, this one. Yeah. So it was x minus 3, but when it's in the parentheses, it reverses on that. So yeah, it should give us a nice asymptote at 3. We'll draw that in. All right, then we'll finish the line. And there we go. Well, that's the graph, but it did ask for the domain and range. So let's start with the domain. We'll show it as an interval, so we don't need any fancy brackets. The domain is the x values. How far to the left does this thing go? 3. That's as far to the left as it goes. But it never actually gets to 3 because that's the asymptote. So it's starting at 3, which is not included. And then how far to the right does it go? Infinity. Alright, well that's the domain. What about the range? How far down does this thing go? Yeah, negative infinity. How far up? Not very fast, but it is going to go all the way to infinity, both of which are not included. So there's our domain and range as well. All right, we'll graph this one and find the domain and range for this one as well. Since this one has that log base 4 of x plus 2, now again we could just plug this into our calculators and find values. We get a lot of decimals though, if we chose values of x. But if we change this into exponential form, then we can find values of y. The problem is that we got that plus 2 there, which can't be with the log to change it back to exponential form. So what I'm going to need to do is subtract 2 on both sides on this thing, which gives me y minus 2 equals log base 4 of x. So now that I have that logarithm all by itself, I can change this into exponential form. But the exponent is going to be all of the left side, which is now y minus 2, right? So I end up with 4 to the power of y minus 2 equals what the log was of, and that's x. So now that we have that exponential form, I would feel better about creating our t-table on this thing. Now I usually start with 0, and you could with y is 0 and solve for the corresponding x value. However, 0 minus 2 is still negative 2, which is going to give us 1 over 4 to the power of 2, which is 16. So 1/16. You know, again, I don't know if that's so helpful, but it's pretty close to 0 already. I put that in the wrong place. There we go. X is 1/16 when y is 0. What I really want to do is make the y value 2, which will make the exponent 0. 2 minus 2 is 0. 4 to the power of 0 is 1. So now I have this point at 1, 2. Alright, let's try something else then. Let's try 3. 3 minus 2 is 1. 4 to the power of 1 is 4. So I got 4, 3. And that should be enough, hopefully, to see the pattern. With the x value being 1/16 when y is 0, we can hopefully see that this is going to get extraordinarily close to the y-axis, but never actually touch it, right? So there's that part of the line. And then it should increase from there, right? If we made y 4, 4 minus 2 is 2, 4 to the power of 2 is 16. So that's pretty far to the right. So we'll just show it going across this way. And that's our line. Now if we look back at this, just the original function, we had log base 4 of x plus 2. And what did it really do? It really moved this up, right? Because originally it would have had this point at 1, 0, but it's been moved up right here to 1, 2. So, and again, that's because we added 2 right there outside of the log, which we showed with that little demonstration earlier. The final thing we need is the domain and the range. So the domain, left and right, this has an asymptote at the y-axis, which is where x is 0. So starting at 0, which again it's never going to actually touch, but get very close to, so it's not included. 0, and this goes all the way to the right forever to infinity. The range is up and down, and we can see this one goes down pretty fast. So it goes to negative infinity. Now this looks like it's kind of leveling out right here, but it will always still increase upwards, which means it's going to go all the way to infinity. There it is.